This is VLSI data conversion circuits, lecture 16. In the last class, what we saw was how one could characterize the static input output characteristics of a quantizer, right. We saw several non-idealities that could occur in practice, which seem perfectly reasonable. One, of course, is that we would like in principle a uniform staircase. The first thing that we can think about is that the staircases is shifted parallel to the ideal one we want, and this in mathematical terms can be modeled as an ideal quantizer with an offset upfront. The next thing one could think of is that the staircase starts off at the right place, but the step size, even though it is the same for all steps, is different from the ideal step size, and then we saw that this would lead to a staircase whose average slope is different from what you want, and this can be modeled by a gain error, right. The third one, of course, is when the step sizes are all different and are not the same as the ideal one that you want, and this will lead to the so called differential and integral nonlinearities. And we saw last time that a differential nonlinearity is trying to give you an indication of the local slope, right, because it is giving information about the deviation of the actual step size from the ideal step size and normalizing it to the average LSB of the quantizer. The integral nonlinearity, on the other hand, is giving you an idea about how far one cotransition lies from the ideal transition. Of course, none of these non-idealities occur in isolation. Any practical converter, A to D converter that we take and measure will have all these together. It will be affected by offset, it will be affected by gain error, and of course the step sizes will not be uniform. And the last time around we saw that differential nonlinearity and integral nonlinearity are two ways of conveying the same information. Given one, we can find the other, right. However, these are ways of representing the transition points of each of these codes in a visually appealing way, in the sense that they immediately give us an idea of what is wrong with this characteristic. As we discussed last time, it does not help too much if you would simply draw the characteristics themselves, right. All that you will see is, you will see something which looks like a staircase, right, with the levels slightly shifted apart, and that is not of it is very difficult to discern what is really going on. What we would be more interested in is what the deviations are from the ideal values, which is why a DNL curve and an INL curve are important and are quoted on all Nyquist rate A to D converter data sheets. Okay. All right. So, the next thing to do is to look at the spectral properties of quantized signals. Okay. So, we will do that today. So, as we have seen, the input output characteristic of the quantizer is a horribly nonlinear affair because of the steps in the characteristic, and whenever you have discontinuities in the characteristic, you know that mathematically this is going to be a very difficult beast to deal with, right. So, let us do this anyway. So, this is the input and this is the quantized input. Okay. and clearly if the quantizer is not overloaded, then what happens? We can say that the difference between the input and the output is, let us assume that we have a quantizer which is ideal. In other words, the step size is uniform, there is no offset, there is no gain error, all that stuff. So, each, let us further denote each step by delta. In other words, the width of each code is the same and equal to delta. Now, if we are in the no overload region of the quantizer, in other words, we are in that part of the staircase which is not flat, okay, then what can we say about the input and the output? First of all, is there a loss of information? Yes. Why? I mean, several values of the input result in the same output. So, given the output, we cannot find uniquely what the input is. So, there is definitely a loss of information, right. The next thing to find, I mean, the next observation is that if we are not overloading the quantizer, then clearly the output is not the same as the input. So, there is some error which we call the quantization. Let me call this, since we are dealing with samples, let me denote them by n rather than t. So, x q minus x in is nothing but the quantization error. And can we make any comment about this quantization error if we know that we are not overloading the quantizer? Clearly, the quantization error, if we have not overloaded the quantizer, is bounded by the step size, correct. So, x q minus x in is bounded in the region minus delta by 2 to delta by 2. Correct. Then let me also draw your attention to the following. Is this quantization error correlated with the input? And what we understand loosely by correlation? In other words, given the input, can we predict the quantization noise, a quantization error at this point? If we know the characteristic of the quantizer, which I am assuming we will know, right. If we know the characteristics of the quantizer and if we know the input, clearly x q minus x n is a known quantity, correct, because given x in we can find x q, which means that you can find x q minus x n, which means that the quantization error is a deterministic signal, it is not random, you understand. So, quantization error is definitely deterministic in nature. can you so if you plot the transfer function of the error, so this is the transfer function of the quantizer or the transfer curve of the quantizer. If I plot the error, which is x in subtracted from x q, this is the quantization error, and how do you think this curve would look like? So, if we are in the no overload region, this must look like a sawtooth type signal, bounded from above by delta by 2 and bounded below by minus delta by 2, correct. So, if one wants to find the spectrum of the output of the quantizer when the input is a sinusoid, how would one go about it? In other words, if x in was a sinusoid of the form say some a cos 2 pi or let me call this some cos a times n is the sequence, and I would like to find the spectrum of x q of n, which is a quantized version of a cos of small a times n. How would we go about it, and what should we expect before we actually go and do this? We know that x q is nothing but x in plus quantization error, and this quantization error can be found by simply taking the input and passing it through a box whose transfer curve looks like this, is not it? Okay. So, if you now take a sinusoid and pass it through a block, can you comment on if the block is linear or non-linear? This is a black box. The input output transfer curve of the black box looks like this. Is this a linear system or a non-linear system? It is clearly non-linear, right. So, what must you expect if you take a pure sinusoid and pass it through such a transfer curve? The output will have a lot of harmonics, okay. So, one thing we must expect, and especially given that the transfer curve has got a lot of discontinuities, you must expect that the quantized sinusoid will have many harmonics of the input. Does that make sense? Okay. And before we actually take a look at the spectrum, finding the harmonic content of a sinusoid when passed through a quantizer turns out is quite understandably not a very easy problem to tackle because of the big discontinuities in the transfer curve, okay. So, it turns out that you end up with Bessel functions, and the math is actually quite complicated, okay. So, a lot of so in other words the going really gets very tough because of the mathematical difficulties involved with first of all, I mean a nonlinear system is bad enough, and now you have nonlinear systems with discontinuities. So you can imagine that finding the Fourier series coefficients of a sinusoid transformed by such a curve is not going to be very simple. Okay. So when the going gets tough, as they say, the tough get going, right. So when the going gets tough, engineers begin to make all sorts of approximations which may or may not be valid, right, but at least it is a way to move forward without dealing with a lot of heavy math. Okay. Surprisingly, in the, I mean, it is not some approach that I would encourage you to take in all situations, right, but in this particular case it turns out that the assumptions which I will show you, which are quite shocking actually, they actually work in practice, and every time you make a phone call, this assumption is being put to test many times. Okay. All right. So given the difficulty of dealing with quantization error, given the whole process is so nonlinear, even for a sinusoid it is actually quite messy. You can imagine what will happen when you have a real signal which is not a sinusoid. If I had a sinusoid, if that was all I had to convey, then there is no information in the sinusoid itself, right. So if we begin to make a couple of assumptions. The first thing is we treat quantization noise, a quantization error, as noise. Okay. So in other words, we say that, oh, there is yeah, sure enough there's a step shape discontinuity in the input output characteristic, but we don't really worry about it. We say the input after getting through this box is getting corrupted by some noise, and since we call this box a quantizer, we call this noise a quantization noise. Okay. So we say, all right, this is so complicated, I do not understand it, let me just call it noise, and it's once I call it noise, I am justified at least in saying that the output is input plus some waveform, that waveform is what I term as noise. Okay. Then I make the first of my bold assumptions, which are A, the noise is independent of the signal, okay. I mean, is this a correct assumption, or it is not a correct assumption? It is clearly not correct, because we just discussed a few minutes ago that given the input and the nature of the quantizer, I can find the output, which means that I can find the error. In other words, the quantization error, the last thing about it is that it is independent of the input. You understand? So the first assumption is we say, hey, noise is independent of the input, okay, and well, at least you can say when you look at the output waveform, it looks so messy that it does not remind us of the input anyway, all right, and then you say, okay, it does not. The next thing is you say the error is bounded between, we know for sure that the error is bounded between plus or minus delta by 2. Then we say, okay, the error is bounded, but we also assume that the error is uniformly distributed between minus delta by 2 and delta by 2. please note that this is also a very big assumption without too much of a mathematical basis, right. I mean, it turns out with that with many real signals this is a fairly decent one, but at this point I mean it seems like a big stretch, all right, because you can find any number of PDFs between minus delta by 2 and delta by 2. Apart from making the math and our lives more simple, there seems to be no particular motivation for choosing a uniform PDF for the error, okay. The third assumption, given that we have made two glaringly wrong assumptions, okay, it does not hurt to make one more, right, which is the quantization error spectrum is white. In other words, the quantization noise is independent from this is the so called white noise assumption of the you must bear in mind that these are again, as I said, engineering approximations which work very well in practice, okay, justifying their use, okay, all right. Of course, the more mathematically inclined of my colleagues will squirm when I start making loose statements like this, okay, but you know it works in practice. That is the only justification we all have. One can of course go and do the math, as I say, but it basically all that it boils down to is it leads to a lot of you know long many pages of algebra, and finally it is not clear whether you know it makes a big difference in practice. The fact that you know that the error is not uniformly distributed, it's not clear if it helps in practice, okay, is knowing it that it is not does not really help in practice is what I am intending to say. So these are the ground rules by which we simply work, and as I said, the justification for this is that they work in practice, okay. Now if the quantization error is uniform in minus delta by 2 and delta by 2, what does this mean for the, so we say that it is noise, it is independent of the input, it is white, it is uniform in minus delta by 2 to delta by 2, which means that the mean square value of this quantization noise process is therefore delta square by 12 is the variance of the noise. And if we have an n bit quantizer, how many steps are there? There are 2 raised, the range of the quantizer is 2 raised to the n, which means what is the maximum sinusoidal amplitude that I can have which fits the entire range of the quantizer? Very good. So the maximum amplitude of the sine wave is 2 to the n minus 1 delta. So the entire range of the quantizer is 2 to the n delta. So what is the maximum signal power that you can pump in without saturating the quantizer? For a sinusoid, you know that amplitude square by 2 is the power. So 2 to the n minus 1 whole square times delta square by 2 is the signal power. What about the quantization noise power? Delta square by 12. So, the signal to quantization noise ratio, so called the SQNR, is the ratio of the signal power to the quantization noise power, and that is two to the n minus 1 whole square by 2 times 12, which is 6 times 2 to the 2n minus 3. Does it make sense? Am I missing something here? Oh, sorry. Yeah, sorry. Okay. Now, so the SQNR is 6 times 2 to the 2n minus 2, and in dB this turns out to be 6.02 n plus 1.76 dB. Since we are, I would like to remind you that since you are taking the ratio of the powers, the logarithm should be to the base of 10, not 20, right. Okay. So, every increase in the bit in the number of bits will increase the signal to quantization noise ratio by 6 dB. So, why does this make intuitive sense? Six dB is if noise signal to noise ratio increases by 6 dB, what is it in real terms? I mean, reduction in signal to quantization noise ratio by 6 dB is equivalent to, if we normalize with respect to the signal power, it means that the noise power has gone down by a factor of 4, right. Noise power has gone down by a factor of 4, and that makes intuitive sense, because if we increase the resolution by 1 bit, it means that the step size has gone down by a factor of 2, correct. So, if the step size has gone down by a factor of 2, the power of the error must have gone down by a factor of 4, right, which therefore means that the noise power has gone down by a factor of 4, which is 6 dB, right. So, increase n by 1 bit, and this means that LSB size goes down by a factor of 2, which means that quantization noise power goes down by a factor of 4, which is 6 dB, right, and therefore, this makes sense. All right. So, if we take a sinusoid quantize it and plot the FFT of the sequence, what would we expect? It is understood that the FFT must be done properly. In other words, the input and the sampling rate must be chosen to be proper, so that there is no leakage and all this other stuff that we have learned so far. So, let us assume that all that is in place. What would we expect when we look at the FFT? We should see the signal, and because we have assumed that there is no leakage, you will see it only in one bin, and if all the assumptions that we made were true, right, white noise, uniformly distributed and all this stuff, we should expect to see a quantization noise spectrum which is flat throughout the. So, if I took an n point FFT, there would be exactly n by 2 bins that I am interested in, right. So, this is 0, this will be the n by 2th bin, correct. So, this should be the input signal and this is the quantization noise. So, how would one compute the signal to quantization noise ratio given this spectrum and nothing else? If for example, I gave you this picture and told you to go and compute the number of bits in the quantizer, how would you go about doing it? Yes. Very good. So, we know that the signal to quantization noise ratio is given by this expression given the input is sinusoidal, right. We know that it is 6.02 n plus 1.76 dB, and if the spectrum is given, what one would do to find the number of levels in the quantizer is to find the signal to quantization noise ratio. And how would one measure this signal to quantization noise ratio given this picture? The signal power is simply the power in this bin, right. The noise power is the power of the noise in all the other bins, okay. You may want to get rid of the DC bin because that may be coming from offset in the converter, right, but you add up the powers of all the other bins, okay, and the ratio of the two will give you the SQNR, and you can compute that in dB and then correlate that with 6.02 n plus 1.76, okay, you understand. So, a very common misconception is to say, oh, I look at this level here, I look at this level here, I look at that distance, right, in dB, oh, and I conclude that that is my SQNR. That is clearly a very a wrong thing to do, right, because what you need to do is actually add up the noise powers in all the bins, okay. In this, for a given quantizer, if I keep increasing the number of bins, what will happen to this distance? Same quantizer, if I went on increasing the number of FFT bins, what do you think will happen to that distance shown in blue? It will go on increasing because the total power is fixed and equal to delta square by 12. If you have a larger number of bins, then the power per bin will reduce. In fact, if you double the number of bins, the height of the noise floor will go down by about 3 dB, correct, because the same power now has to be spread across twice the number of bins. So, in each bin it will go down by 3 dB. So, this height in blue is just can be arbitrarily increased by going on increasing the number of bins over which you compute the FFT. However, for a given ideal quantizer, the power of noise when you compute it across all the bins must remain the same and equal to delta square by 12. Is that clear? All right. So, in practice, of course, we know that the quantizer staircase is not quite as nice as we would want it to be. First of all, the step size is not uniform, there may be gain error, all sorts of things. So, when you actually take a real converter and plot its spectrum, apart from the sinusoid at the input, you will also see harmonics, okay, and some of the harmonics, the higher harmonics may actually alias back and will look like low frequency tones, you understand, okay. Clearly the harmonics of the sample and hold for example will lie well beyond Nyquist, right. So, when you sample it at Fs, they will alias back and so on. And so, when you actually take a real quantizer with all sorts of non-idealities and make a diagram like this, and when you actually compute the signal to quantization noise ratio, you will find that the actual SQNR is smaller than what you expected. Let us say you designed a 10-bit converter, which means that in principle you would be expecting a signal to quantization noise ratio of about 61.76 dB or so, all right. But in spite of having a 10-bit quantizer, and when you actually made it, let us say you got only 45 dB, you understand, due to say bad design or some other non-idealities. But this is indeed a 10-bit converter in the sense that 10 wires come out of the box, okay. So, clearly we need a metric to not just just because 10 wires are coming out of a box, that does not mean that this is a 10-bit converter, all right. So, my converter may give you 50 dB, his converter may give you 51 dB, all of them being nominally 10-bit converters, okay. So, there is a need for not just saying, oh, my A to D converter box has got 10 wires coming out of it, right. You need a more scientific method of qualifying the performance of the A to D converter, right. So, one such metric is called the effective number of bits or the ENOB of the converter. And for this, what do you suggest we do? That is all. So, the definition is quite straightforward. We take the actual signal to quantization noise ratio that we measure, right. From this we subtract 1.76 and divide by 6.02, and this would give the effective number of bits. And to compute the signal to quantization noise ratio, the input signal power is clearly, there is no ambiguity there, and often the rest of it, whether it is distortion or quantization noise, you combine all the bins and that is taken as the noise power. You compute the signal to noise ratio that way and you subtract 1.76 and divide by 6.02, okay. You will find that for Nyquist converters, if you design for a resolution, you will always get an effective number of bits which are smaller than what you designed for. If you design a 10-bit converter, A very good 10 bit converter will probably give you say 9.5 bits, okay, whereas a poor converter will give you an effective resolution which is lot smaller than 10 bits. This effective resolution also depends on the input frequency. So, when the input frequency to the converter is very small, in other words the input frequency is very small compared to Fs by 2, then presumably it is easier to make circuits work because the input remains the same from sample to sample. So, circuits inside do not have to work quite as hard as they do when the input is changing rapidly. So, you will find in general that the E knob of the converter or the effective number of bits of the converter keeps falling with input frequency. Okay, this is something to be expected. Of course, if you have a very good design, then the fall will be hopefully very small. Okay. So, all these metrics are quoted whenever you report a converter or when you buy a converter, the manufacturer will give you these numbers and these curves as a function of frequency, so that you can be sure if it is good enough for the application you are targeting. Okay. All right. So, now again please note that this uniform the white assumption for the quantization noise is what has prompted us to assume that the quantization noise spectrum for an ideal quantizer is going to be flat. Okay. Now, let us take a sinusoid, quantize it and take a look at the spectrum and see what we get. So, this is a sinusoid shown in blue. The red one is the quantized sinusoid. The picture in the curve in magenta is the quantization error, and clearly as you can see, when the input is varying rapidly, you can see a sawtooth type waveform. At the tops of the sinusoid you can see a waveform which varies a little more gently, okay. But it does not take a genius to figure out that the frequency content of the quantization noise is, when you must expect it to have a lot of high frequency content. See, one useful mathematical equivalence is the following: whether you take a signal, sample it and quantize it, or you take a signal, you quantize it and sample it later, the end sequence will have the if I put both these inside a black box, you will not be able to tell me which is which. In other words, the sequence at the end has the same spectral properties, is identical in other words. Okay. So, sometimes it is useful to think of quantization this way, where we say we take a sinusoid, we quantize it, this is all now in continuous time, and then we sample the quantized continuous time signal. Clearly the quantized signal will have a whole bunch of harmonics because of the nonlinear operations preceding, that are going on inside the quantizer, and clearly these harmonics will not satisfy the Nyquist criterion even if the input does. So, the moment you sample spectra from, and all these harmonics will all alias back into the range 0 to Fs by 2, okay, and will produce some spectrum in that region. Okay. So, this corresponds, this particular picture corresponds to a LSB size or step size of 2 by 8, and why I write 2 by 8 rather than 1 by 4 is that this entire signal range is assumed to be from -1 to 1, and I have divided that up into 8 steps. okay, 8 bins rather. Okay. All right. Now, I repeat the same experiment with delta is now 2 by 16. I have increased the number of levels by a factor of 2. All right. Now, one thing that you can observe is that the height of this error has gone down by a factor of 2 when I increase the resolution by 1 bit. Please note that this is an increase in the resolution by 1 bit because I doubled the number of levels. Okay. Now, when I look at the spectrum of one of these guys, we see that this quantization, I mean this is the input signal and all this stuff is quantization noise, and not surprisingly we see that it is not very, it is not quite as flat as we expected, and that makes sense because we made a whole bunch of questionable assumptions, and when you plot the spectrum, the quantization noise spectrum is not quite as flat as we expect. There are, you can see many spikes in the spectrum, okay, and this makes sense because basically this is a deterministic process, and you have gone and I mean all these, you generate a whole bunch of harmonics, and some of them when they all alias back into 0 to fs by 2. So, these are all harmonics of the input which have aliased back. Okay. Now, it is interesting to compare the spectra of the same sinusoid passed through two different quantizers. Please note that in both these cases I have taken a 4096 point FFT, and the input signal is related to Fs by a rational number 19 by 4096. So, the input therefore lies on 1 bin. Do I need to be worried about FFT leakage at all, given that there is noise as well as signal? Why not now?
Because in this case, Fn by Fs is the ratio of integers.
Okay.
So
All right. Yes, I mean, if this noise was shaped, then discontinuities at the edges, as we saw, will cause filling up of those notches in the spectrum, right. Another thing here is that even though we think of this as noise, in reality this is a deterministic phenomenon. So, the quantization noise is actually periodic with the record lengths, correct. The input is periodic, which means that the quantization noise must also be periodic, because the quantization noise is a deterministic signal which depends on the input. So, we do not have to worry about leakage at all, you understand. Now, given that the ratio of the input to the sampling rate is 19 by 4096, which is a very small number, I do not know if you are able to discern this, but that is the input. Can you tell me, so one of them corresponds to an LSB of 2 by 8 and the other one corresponds to an LSB of 2 by 16. Can you tell me which spectrum corresponds to an LSB size of 2 by 8 and which corresponds to 2 by 16? The one on the left corresponds to 2 by 8, and why would that be? Well, visually it seems as if the noise spectrum here, when you integrate all the power in all these tones, is larger than the noise you might get when you integrate the power in all these tones, right. Okay. So, that is definitely correct. In the next class we will take a look at some other important aspects of a couple of more things that we can intuitively find from these spectral diagrams and see why they make sense. Okay. Thank you.